Astronomers just discovered an asteroid that breaks the laws of physics as we understand them. It is 710 meters wide, nearly half a mile across. It completes one rotation every 1.88 minutes, and it is made of solid rock. Published January 7, 2026, in the astrophysical journal Letters, this is the first peer-reviewed science result from the Vera C. Rubin Observatory. Right now, this asteroid, designated 2025 MN45, is orbiting in the main asteroid belt between Mars and Jupiter. Every 113 seconds, it completes a full rotation. That spin rate should tear it apart. For an asteroid larger than 500 meters to spin that fast and remain intact, it must have cohesive strength similar to solid rock. But most asteroids are rubble piles, collections of smaller rocks held together only by gravity. 2025. MN45 should not exist. The discovery came from analyzing data collected during the commissioning phase of Rubin Observatory's LSST camera, the largest digital camera in the world, in April and May 2025. The camera captured light curves showing how the asteroid's brightness fluctuates as it spins. Those light curves revealed not just 2025 MN45, but 18 other fast-rotating asteroids, all larger than 90 meters, all spinning faster than the theoretical limit for rubble piles. Dr. Sarah Greenstreet from NORLab, lead author of the study, stated, "Clearly, this asteroid must be made of material that has very high strength in order to keep it in one piece as it spins so rapidly. We calculate that it would need a cohesive strength similar to that of solid rock." This is somewhat surprising since most asteroids are believed to be what we call rubble pile asteroids. Still more striking, the team believes 2025 MN45 is a collisional fragment from a much larger parent body that was heated and differentiated early in the solar system's history. The parent body melted internally, separating into a dense metallic core, a rocky mantle, and a lighter crust. A catastrophic collision shattered the parent body, and 2025 MN45 was ejected from the core region. That explains its high density and solid structure. It is a piece of a protoplanet's core spinning through space. Here is what should concern you most. If 2025 MN45 is a core fragment, then many other fast-spinning asteroids may also be fragments from differentiated parent bodies. The asteroid belt contains remnants of dozens or hundreds of destroyed protoplanets. And the rubble pile model, which has dominated asteroid science for decades, may not apply to all large asteroids. Some are solid, some are rubble. And we cannot tell which is which without measuring their rotation rates. Think about that. Before we explain how astronomers found an asteroid spinning faster than it should be able to, if you want to stay updated on discoveries from the Vera C. Rubin Observatory as it begins its 10-year survey of the night sky, hit subscribe and turn on notifications. Because what we are about to reveal will change how you think about asteroid structure and the violent history of the early solar system. Leave a comment telling us, did you know that most asteroids are rubble piles held together only by gravity, and that solid asteroids are rare? Let's start with what an asteroid actually is. Asteroids are rocky bodies orbiting the Sun, primarily concentrated in the main asteroid belt between Mars and Jupiter. They range in size from a few meters to hundreds of kilometers. The largest asteroid series is approximately 940 kilometers in diameter and is classified as a dwarf planet. Most asteroids are much smaller. Asteroids are remnants of the early solar system. When the solar system formed 4.6 billion years ago, the protoplanetary disk contained vast amounts of dust and gas. In the inner solar system, that material coalesced into planetesimals, small rocky bodies that collided and merged to form the terrestrial planets, Mercury, Venus, Earth, and Mars. In the outer solar system, beyond the snowline where water ice could condense, planetesimals grew larger and accreted gas to form the gas giants, Jupiter, Saturn, Uranus, and Neptune. The asteroid belt is the region where planetesimals failed to coalesce into a planet. Jupiter's gravity prevented the material in the belt from accumulating into a single large body. Instead, collisions fragmented planetesimals, creating a population of smaller asteroids. Over billions of years, collisions continued, grinding down large asteroids and producing smaller fragments. That collision history is why most asteroids are rubble piles. When two asteroids collide, the impact shatters both bodies into fragments. Gravity then pulls the fragments back together, but the resulting object is not a coherent solid rock. It is a loose collection of smaller rocks, boulders, and dust held together by weak gravitational attraction. The interior has voids, gaps, and no structural strength beyond the friction between individual fragments. But there is a fundamental limit to how fast a rubble pile can spin. But the mysteries don't stop there. The limit is called the spin barrier. For a rubble pile asteroid, centrifugal force from rotation acts outward, opposing gravity. If the rotation is too fast, centrifugal force exceeds gravity, and the asteroid flies apart. The critical rotation period depends on the asteroid's density. For typical asteroid densities of 2,000 to 3,000 kilograms per cubic meter, the spin barrier is approximately 2.2 hours. Any asteroid spinning faster than 2.2 hours must have internal cohesion beyond gravity alone. For decades, astronomers observed that large asteroids rarely spin faster than 2.2 hours. That supported the rubble pile model. Smaller asteroids, below about 200 meters in diameter, can spin faster because they can be monolithic rocks, single solid pieces formed from collisional fragments. But large asteroids, those larger than 500 meters, were thought to always be rubble piles. The spin barrier was first recognized in the early 2000s when large surveys began measuring asteroid rotation periods systematically. The Sloan Digital Sky Survey and other ground-based programs accumulated data on thousands of asteroids. When rotation periods were plotted against asteroid size, a clear pattern emerged. Small asteroids had a wide range of rotation periods, including very fast ones, while large asteroids almost never spun faster than 2.2 hours. The explanation seemed obvious. Small asteroids, formed as intact fragments from collisions, could be solid. Large asteroids, formed from reaccumulation of collision debris, were rubble piles. The 2.2-hour limit was the spin barrier for rubble piles. Any large asteroid spinning faster would fly apart. But there were hints that the picture was incomplete. A few large asteroids were observed spinning slightly faster than 2.2 hours. Those objects were outliers, difficult to explain. Some researchers proposed that they might have unusual shapes or internal structures that allowed them to spin faster without disrupting. But without detailed observations, the nature of those outliers remained uncertain. The Rubin Observatory's discovery of 19 fast rotators, including 2025 MN45 with its extreme 1.88-minute period, proves that fast-spinning large asteroids are not rare outliers. They are a distinct population, and they require a new explanation. They are solid, not rubble piles. 2025 MN45 shatters that assumption. At 710 meters in diameter, it is far above the 500-meter threshold, and it spins with a period of 1.88 minutes, far faster than the 2.2-hour barrier. It cannot be a rubble pile. It must be solid. How do we know its size and rotation period? The answer lies in light curves. A light curve is a graph showing how an object's brightness changes over time. For an asteroid, brightness fluctuates as it rotates because different parts of its surface reflect different amounts of sunlight. If one side is brighter than the other, the asteroid appears brighter when that side faces Earth and dimmer when it faces away. By observing an asteroid over multiple rotations and recording its brightness at regular intervals, astronomers can determine the rotation period. The period is the time it takes for the light curve to repeat. For 2025 MN45, the Vera C. Rubin Observatory captured enough data points to measure a rotation period of 1.88 minutes with high precision. The light curve also provides information about the asteroid's shape. If the asteroid is elongated, the brightness variation is larger because the projected area changes significantly as it rotates. If the asteroid is nearly spherical, the brightness variation is smaller. 2025 MN45 shows a moderate brightness variation, suggesting it is somewhat elongated but not extremely so. Here's where it gets really strange. The size estimate comes from combining the light curve with assumptions about the asteroid's albedo, the fraction of sunlight it reflects. Albedo depends on surface composition. Dark carbonaceous asteroids have albedos around 0.05, reflecting only 5% of sunlight. Brighter rocky asteroids have albedos around 0.2 to 0.3. By assuming a typical albedo for main belt asteroids and measuring the asteroid's apparent brightness, astronomers can estimate its size. For 2025 MN45, the estimated diameter is 710 meters, with some uncertainty depending on the true albedo. The Vera C. Rubin Observatory is uniquely suited for discovering fast-rotating asteroids. The observatory's LSST camera is the largest digital camera in the world, with 3.2 billion pixels. It can image large areas of sky quickly and return to the same regions frequently. That is critical for detecting asteroids and measuring their light curves. The camera's specifications are extraordinary. The focal plane contains 189 individual charge-coupled devices, CCDs, arranged in a grid. Each CCD has 16 megapixels, and together they produce images with 3.2 gigapixels. The field of view is 9.6 square degrees, approximately 40 times the area of the full moon. That wide field allows the camera to survey large portions of sky in each exposure. The camera is housed inside the Simony Survey Telescope, an 8.4-meter telescope on Cerro Pachón in Chile. The telescope's design uses a 3-mirror system that provides excellent image quality across the entire focal plane. The system can take 15-second exposures and move to the next field within seconds, enabling rapid surveys. The LSST Legacy Survey of Space and Time will observe the entire visible southern hemisphere sky every few nights for 10 years. Each region of sky will be imaged hundreds of times, allowing astronomers to detect transient and moving objects. Asteroids move relative to background stars, so they appear in different positions in sequential images. By comparing images taken minutes, hours, or days apart, the survey can identify asteroids and track their motions. The 20 terabytes of data generated each night is more than 350 times the data produced by JWST. Processing that data requires advanced algorithms to detect moving objects, measure their positions and brightnesses, and link detections across multiple nights to determine orbits. The Rubin Observatory has developed sophisticated software pipelines to handle the data volume and deliver science-ready products to the astronomical community. During the commissioning phase in spring 2025, the observatory conducted test observations to verify the camera's performance. Those observations covered portions of the sky repeatedly over several nights. Asteroids move relative to background stars, so they appear in slightly different positions in each image. By tracking moving objects and recording their brightness, the observatory identified thousands of asteroids, approximately 1/1900 of which had never been observed before. Dr. Sarah Greenstreet and her team analyzed the light curves of those asteroids to determine rotation periods. They identified 76 asteroids with reliable rotation periods, including 19 that spin faster than 2.2 hours. Of those 19, 3 are classified as ultra-fast rotators, spinning faster than 1 hour. 2025 MN45 is the largest and fastest of all. A close second is 2025 MJ71, which spins with a period of 1.9 minutes, nearly as fast as 2025 MN45. The fact that 2 asteroids spin at such similar extreme rates suggests they may have similar origins. Both could be collisional fragments from differentiated parent bodies. The other 17 fast rotators span a range of rotation periods. 2025 MK41 spins every 3.8 minutes. 2025 MV71 rotates every 13 minutes. 2025 MG56 completes a rotation every 16 minutes. All 19 asteroids spin faster than the 2.2-hour Rubble pile barrier, but they show a diversity of rotation rates. That diversity suggests different formation mechanisms or different parent body properties. Some may be core fragments like 2025 MN45. Others may be mantle fragments, which would be less dense but still solid. Still others may be smaller fragments ejected at higher velocities, explaining their faster spins. The population of fast rotators is not homogeneous. Each asteroid has its own history, its own parent body, and its own collisional origin. And the data showed something that simulations hinted at, but observations had not confirmed. The discovery of 19 fast-rotating asteroids in a single dataset is significant. Previous surveys had found only a handful of fast rotators in the main belt. Most known fast rotators are near-Earth asteroids, which are easier to observe because they pass close to Earth. Main belt asteroids are farther away and fainter, making their light curves harder to measure. The Rubin Observatory's sensitivity and rapid cadence overcome those limitations. Dr. Luca Rizzi, an NSF program director, noted, "NSF DOE Rubin Observatory will find things that no one even knew to look for." Regina Ramica, the DOE's associate director for high-energy physics, added, "Discoveries like this exceptionally fast-rotating asteroid are a direct result of the observatory's unique capability to provide high-resolution, time-domain astronomical data, pushing the boundaries of what was previously observable." The collisional fragment hypothesis explains why 2025 MN45 is solid. The hypothesis proposes that 2025 MN45 originated from a large parent body, possibly hundreds of kilometers in diameter, that formed early in the solar system's history. That parent body was large enough to generate internal heat from radioactive decay and gravitational compression. The interior melted, and denser materials sank to the center while lighter materials rose to the surface. The parent body differentiated into a metallic iron-nickel core, a rocky silicate mantle, and a lighter crust, similar to the structure of Earth or other terrestrial planets. Why did the parent body melt? In the early solar system, short-lived radioactive isotopes like aluminum-26 and iron-60 were abundant. Those isotopes decay with half-lives of less than 1 million years, releasing energy. If a planetesimal accreted quickly, within a few million years of the solar system's formation, it would trap those isotopes inside. The decay heat raised the interior temperature high enough to melt rock and metal. Once melted, the material separated by density. Iron and nickel, being denser, sank to the center, forming a metallic core. Lighter silicates remained in the mantle. The lightest materials, including volatiles and low-density minerals, rose to the surface, forming a crust. This process, called differentiation, is how planets and large moons develop layered structures. Not all asteroids differentiated. Only those that formed early and grew large enough to retain heat underwent differentiation. Smaller bodies, or bodies that formed later, after radioactive isotopes had decayed, remained undifferentiated. The asteroid belt contains both differentiated and undifferentiated bodies. Meteorites provide direct evidence. Some meteorites, like iron meteorites, come from differentiated cores, while others, like chondrites, come from undifferentiated parent bodies. When a differentiated parent body is shattered by a collision, the fragments retain their internal structure. Core fragments are solid metal or dense rock. Mantle fragments are rocky. Crust fragments are lighter. 2025 MN45's high density and rapid spin suggested is a core or mantle fragment, not a crust fragment. Later, a catastrophic collision shattered the parent body. The impact was energetic enough to break the body into many fragments, scattering them throughout the asteroid belt. Some fragments came from the crust, others from the mantle, and still others from the core. 2025 MN45 is believed to be a core fragment because its high density and solid structure are consistent with metallic or dense rocky material from a differentiated core. The collision also imparted angular momentum to the fragments, causing them to spin. If the collision occurred at high velocity and the fragment was ejected with significant rotational energy, it could end up spinning very rapidly. Once ejected, there is no mechanism to slow its rotation unless it experiences another collision or tidal interactions with a massive body. In the main asteroid belt, collisions are infrequent, and tidal interactions are negligible because the sun's influence is weak at that distance. So 2025 MN45 has retained its rapid spin for billions of years. Could the rotation have been accelerated after ejection? There is a phenomenon called the Yorp effect, Yarkovsky-O'Keefe-Radzievsky-Paddock effect, where sunlight absorbed and re-emitted by an asteroid creates a small torque that can spin up or spin down the rotation over millions of years. Yorp has been observed to change rotation periods of small asteroids measurably over decades. However, Yorp is most effective for small, irregularly shaped asteroids with sizes below 10 kilometers. For a 710-meter asteroid like 2025 MN45, Yorp could contribute to changes in rotation over very long timescales, but it is unlikely to be the primary mechanism that accelerated it to such an extreme spin rate. The initial angular momentum from the collision is the more plausible explanation. Additionally, Yorp can both speed up and slow down rotation depending on the asteroid's shape and spin axis orientation. If 2025 MN45 had been spun up by Yorp, other similar asteroids should also show evidence of Yorp spin-up. But the 19 fast rotators discovered by Rubin show a range of rotation periods and do not cluster around values that would suggest Yorp as the dominant mechanism. The diversity of rotation periods supports the collisional origin hypothesis. This scenario is not unique to 2025 MN45. The asteroid belt likely contains many core fragments from differentiated parent bodies. Some of those fragments may be fast rotators, others may spin more slowly. The key is that solid asteroids can spin much faster than rubble piles without flying apart. But there's another problem that nobody expected. How common are solid asteroids versus rubble piles? We do not know. Most asteroids have not had their internal structures measured. Rotation period is one clue, but it is not definitive. An asteroid spinning slower than 2.2 hours could be either a slow-spinning solid asteroid or a rubble pile. Only asteroids spinning faster than 2.2 hours can be confidently identified as solid. The Vera C. Rubin Observatory will help answer that question. Over its 10-year legacy survey of space and time, LSST, the observatory will observe the entire visible southern hemisphere sky every few nights, generating light curves for millions of asteroids. By measuring rotation periods for a large sample, astronomers will determine what fraction of asteroids are fast rotators and, by extension, what fraction are solid. That has implications for planetary defense. If an asteroid is on a collision course with Earth, understanding its internal structure is critical for planning a deflection mission. A solid asteroid can be deflected more easily because it responds predictably to impacts or gravitational tugs. A rubble pile is more difficult to deflect because the impact energy disperses through the loosely bound fragments, and the asteroid may break apart instead of changing trajectory. NASA's DART mission, which impacted the asteroid Dimorphos in September 2022, demonstrated kinetic deflection. Dimorphos is believed to be a rubble pile, and the impact successfully changed its orbit. But the debris ejected from the impact was extensive, indicating that the asteroid's structure is loose. For a solid asteroid, the deflection efficiency would be different, and the debris production would be lower. Now let's put everything together. 2025 MN45 is a 710-meter-wide asteroid orbiting in the main asteroid belt. It completes one rotation every 1.88 minutes, making it the fastest spinning asteroid larger than 500 meters ever discovered. It must be made of solid rock or metal to withstand the centrifugal forces without flying apart. The leading hypothesis is that it is a collisional fragment from a differentiated parent body that was shattered billions of years ago. The fragment came from the parent body's dense core and was ejected with high rotational velocity. The discovery was made using data from the Vera C. Rubin Observatory's LSST camera during commissioning observations in spring 2025. The observatory identified 19 fast-rotating asteroids, all larger than 90 meters, in a dataset covering only a few nights of observations. This is the first peer-reviewed scientific result from the Rubin Observatory and demonstrates its capability to discover and characterize asteroids with unprecedented efficiency. The existence of 2025 MN45 challenges the assumption that all large asteroids are rubble piles. Some are solid. Those solid asteroids are likely collisional fragments from differentiated parent bodies. The asteroid belt contains remnants of dozens or hundreds of protoplanets that failed to form into full planets and were later destroyed by collisions. We are not saying that rubble piles do not exist. They do. Most asteroids are rubble piles. But the fast rotators reveal that a significant population of solid asteroids also exists, and that population has been underestimated because fast rotators are difficult to detect. Dr. Greenstreet stated, "As this study demonstrates, even in early commissioning, Rubin is successfully allowing us to study a population of relatively small, very rapidly rotating main belt asteroids that we did not have access to study before." And here is what this really means. The Vera C. Rubin Observatory will revolutionize our understanding of asteroids. Over the next 10 years, it will discover millions of asteroids, measure their rotation periods, and determine their internal structures. The data will reveal how many asteroids are solid, how many are rubble piles, and whether there are distinct populations with different formation histories. So what do we know for certain? 2025 MN45 is 710 meters wide and rotates every 1.88 minutes. It is made of solid rock or metal, not a rubble pile. It was discovered by the Vera C. Rubin Observatory and data collected during commissioning observations in spring 2025. It is one of 19 fast-rotating asteroids identified in the study, published January 7, 2026, in the astrophysical journal Letters. What don't we know? The exact composition of 2025 MN45, whether it is primarily metallic iron nickel or dense silicate rock, the identity of the parent body from which it originated, how common solid asteroids are compared to rubble piles, and whether other fast rotators in the dataset also originated from differentiated parent bodies or whether some formed through different mechanisms. And here is the urgency. The Vera C. Rubin Observatory begins its 10-year legacy survey of space and time in 2026. The survey will observe the sky every few nights, generating 20 terabytes of data per night, more than 350 times the data produced by JWST. Within the first year, the observatory will discover hundreds of thousands of new asteroids and measure rotation periods for tens of thousands. Within a decade, millions of asteroids will have light curves and rotation periods. Because if solid asteroids like 2025 MN45 are common, then our understanding of asteroid structure, formation, and evolution will need to be revised. And if they are rare, then 2025 MN45 is an exceptional object, a piece of a protoplanet's core that has survived for 4.6 billion years, spinning at a rate that should have destroyed it long ago. The truth is this: 2025 MN45 should not exist. By all models of rubble pile asteroids, it should have flown apart billions of years ago. But it is here, it is spinning, and it is solid. That means the asteroid belt is more complex than we thought, and the Vera C Rubin Observatory is just beginning to reveal that complexity. And the only way to understand how common objects like 2025 MN45 are, and what they tell us about the early solar system, is to observe as many asteroids as possible, measure their rotation periods, and determine which are solid and which are rubble piles. If this video changed how you think about asteroids and the violent history of the early solar system, hit like and subscribe to this channel. We are tracking the Vera C Rubin Observatory's legacy survey of space and time as it begins in 2026, and you will not want to miss what it discovers. Leave a comment with your take. Did you know that most asteroids are rubble piles, not solid rocks? And share this video with anyone who thinks asteroids are just big space rocks. After this, they will understand that asteroid structure is diverse, complex, and still not fully understood.